Hi guys. So there's an SI session tonight at 8:30 in Guilford 323, and another one tomorrow in Bingham 103 at 4:30. Come learn chemistry, it's fun. Also, congrats to AKO and SIGEP on winning Greek Week.
Hey guys, my name's Jeremy. I'm one of your chem classmates. I just wanted to let you know this Sunday, the 13th, Fiji is having its philanthropy event. We're having a dodgeball tournament. It's going to be up at Adelbert Gym at 12 o'clock. It's going to be a lot of fun, food prizes. It's $35 for entry fee for a team of 6. We have an ad in the Observer. You can just stop by the house. You can go on the Facebook event, get all the information, just email, sign up your friends. It's going to be a good time, so hope to see a bunch of you out there.
There it is. All right. Finally we got here. So one note. All right. First of all, is this thing, you can hear it, but they can't. That's all right, right? Can you guys hear this thing at all in the back? No, I didn't think so. He can hear it on the tape. It says it's on. All right, let's go without it today. I think I can make my voice last an hour. It shouldn't be too bad. First of all, I had a couple of questions about what's left with the rest of the semester. We do have an exam on Thursday the 17th. It'll be over electrochemistry, thermodynamics, and a little bit of inorganic chemistry. The final exam is Thursday, May 1st. And yes, it is cumulative. Course. It is not over the last week and a half of material. It is over the entire year. But if you think about it, everything's built up to this anyway, so I don't think it's that bad. Your papers are still being graded. I started to get abusive to a few people, and so I decided, okay, I'd rather slow down a little bit and get you a serious grade than to take it out on the people whose papers I happen to be grading at that time. So I took a break for a little bit. I'm going back to it. I'm going to finish them this week so that you guys have them back. A big question was asked about dropping an assessment. There is no limit to what assessment I will drop. In other words, if you want to drop the final exam, that's okay. You can take a 0 on the final exam. What it means is, and that's true for anyone. If you add up your points after the next test, and you're satisfied with your point total, whatever it is, you can skip the final exam, you'll get a 0 on the final, and it won't figure into your grades. However, you will then only have a possible 650 points, because you're throwing away 150 or 50 points on the final exam, because the final exam is worth 150. And so you're going to take a 0 on 50 points that you could have gotten otherwise. But if that's what you want to do, if you sit down and you say, okay, I have, the only way for me to get the next higher grade is to get 140 on the final, That ain't gonna happen. If I take a 0, I'm gonna get the same grade. That's okay, that's your decision. You have to sit and work the math on it. No, because then the 20 will be your low score and you'll drop your final exam score. So you will have all but one assessment counted. And that means is that I have to calculate a percentage for each of the assessments. And whichever one's the lowest percentage is the one that we drop. So no, you can't just get a 20 on final, because that will more than likely be your lowest score. It'll get dropped.
But why is your exam worth, if your final's worth more points? Yeah. Right? And so if I got a, like,
If you get a
30
30,
on the final.
if you get a 35% on the final,
Yeah.
and 35% of 150 is 52,
Yeah.
and your next lowest score is a 53, I'm going to drop the final.
Yeah, but then,
But I have to figure it out in terms of points, right?
yeah, it's taking away more points than if you got the other 50.
But if you're either going to get 52 points from the final or 53 points from the other one, so I'll drop to 52 points. It actually works out to your advantage.
You have not to have a big drop.
Ultimately, you'll get the highest score I can give you. Yeah. So it really makes it so that if you've done very, very well, the final exam is completely optional. So. All right. Whoops. Okay. What's the other thing I need? Bonus points. I'll have a list of those posted to Blackboard on Wednesday. I've got lots of people sending me things they want to do for bonus. That's great. I will give you a list that will last for the rest of the semester then. All right? Questions? Okay. I thought about Yashar's question after I left. Saying, why do we need to know this? What is this electrochemistry stuff? And at one point in the semester, I can't tell you when, but I usually answer this question: why do you do a chemical reaction? You undertake a chemical reaction, A, if you need to make a specific product, B, you need to get rid of something, or C, you need to generate some energy. Electrochemistry is the way that many chemical reactions generate energy. Yes, there's going to be thermal energy in a lot of these, but in electrochemical reaction, what we're going to do is we're going to harness the fact that we've got electrons being transferred, and we're going to take advantage of those electrons being transferred in order to generate current or flow of electrons so that we can do something else. And so what we had talked about here was just a reminder to tell you what you need to do, and I'll post this to Blackboard so you have it. What are the steps you need in order to balance any electrochemical reaction? So here are the 7 steps. The only one that's a little bit odd is this last one that says if you need to neutralize the acid, you do it by adding hydroxide. Now somebody came up afterwards and said, wait a second. That statement doesn't make sense. If basic, neutralize H plus with OH minus. The way these problems are usually explained is, okay, I've got this reaction in acid solution. And so when I balance this reaction, when I'm done with the reaction, I should have H plus somewhere in the equation, or it may not be there at all. Okay? If there's no H plus needed in the reaction, and the example might be this one up on top, copper and zinc, there's no H plus needed, we can assume it's acid solution. If the reaction takes place in a basic solution, we should have hydroxide ions somewhere in the reaction. So all this is saying is, if you know that it's done in an acidic medium, you have to have H plus in there somewhere, or it doesn't appear at all. If it's in basic solution, there should be OH minus somewhere. Okay? Now, the reason that's going to become important is we'll start right here. See if I can move this around, sorry. I have a nice glare and I can't get rid of it. There we go. You can take nickels and pennies and stack them so that there's a penny on top. In between, there's a piece of paper that you've soaked in salty water. Cardboard that comes from the back of a tablet of paper works real well. Followed by a nickel, then a penny, and then the paper, nickel, penny, paper, and so on. And when you take this thing and you take two pieces of wire and connect them on either side, you can actually light a light bulb with this thing. You don't believe me?
Could you just do it with a normal penny?
Could you just do it with a normal penny?
Post 1983 pennies?
Post 1982.
Too.
What Zane's getting at is that, if you want, by the way, there's a website, and if it launches my browser, you'll see it, that tells you exactly how to do this step by step. Try it again? All right, I'll try it again. Oh, that's because I don't, there we go. He just upped the volume. There's a little too much feedback, but we can get rid of that, right? Whoops, unable to open it, why not? Because it's saying I'm not live, but that's all right, we'll try again. If in 1982, pennies changed their composition, as you all know from an earlier exam, right? Now they're a mixture of zinc and copper. All right, I'm not going to go live, but it's on there when I post this. It gives you the step-by-step instructions on how to do this. One of the pages on there says, can I do that? There's another link here that allows you to do it with a lemon and some vinegar. There's a web page on there that shows you how to make a battery out of a single penny. Anytime you mix two metals together, you have the potential to create an electrochemical cell. What's going to happen is one of the metals is going to get oxidized and one is going to get reduced. The question that we have to figure out is, in the case of copper and zinc, or copper and nickel here, which one gets oxidized, which one gets reduced? In the case of a penny, why don't you generate an electrochemical cell just because you've got copper and zinc mixed together? Well, one of the reasons is you have to have something to carry the current between them. Zinc and copper are metals that will interact with each other if there is something to carry the electrons across. And something we need in this case is ions, sodium chloride. If you take just a single penny, and the question then becomes, why doesn't it react with itself? There are no ions present. It's just like on Friday we talked about, how do you keep a car from rusting? You paint it. You remove oxygen from the reaction, you remove salt from the reaction. But if you've got oxygen and salt and iron present, you're likely to get rust. We're going to talk about rust in a little bit. If we do this experiment with magnesium and copper, take a piece of magnesium, piece of copper, and actually literally stick it into a lemon, you can measure a voltage between them of 1.95 volts. If you do the same experiment here, there's a penny and a zinc-coated nail. This one is that reaction we started with earlier. It's called the Daniell cell. It's one of the first ones that was made. It takes copper and zinc. I'm sorry? There's no change in the reaction? Oh, that's not good. I need to ionize something, don't I? I wish these tables were right where I needed them to be. There they are. How's that? Let's try writing a little clearer today. So if I take those two half reactions that are happening in this cell, and I add them together, I should generate about 1 volt of current. I should be able to get 1 volt of potential difference, actually, right, between the two halves of this. The challenge that we have in any electrochemical reaction is, how do we get that current to do what we want it to? So in other words, how do I take a container, what do I have to fill it with? I have to fill it with copper ions. There's copper ions in there. And I have to put a piece of zinc metal in here. And as soon as I do that, then the copper ions will pick up electrons and make copper metal. The zinc metal will lose 2 electrons to give me zinc ions. But this is all going to take place right there. It's not going to do me any good. The electrons are going to flow back and forth between the copper ions in the solution and the zinc metal that's hanging in the solution. So I'm going to try and set this thing up to try to force the electrons to do what I want. And the easiest way to do it is to set up 2 different cells. One of them is going to be filled with copper ions. The other solution can be anything I want it to be, as long as there's a piece of zinc here. Okay? I'm going to put a light bulb right here. And my goal is to try and light that light bulb. The only way to light the light bulb is to get electrons to move through that light bulb. As soon as electrons go through the tungsten wire that's in the light bulb, it'll heat up and start to glow. I already know that copper ions will give up 2 electrons, or will pick up 2 electrons to make copper metal. The zinc will give up some electrons, so I can make this piece of zinc dissolve and give me zinc ions if I can somehow connect these. Well, the easiest thing is let's just take a wire and connect it onto there. And over here we're going to take a wire, and there's nothing to connect it to. I could just hang the wire into the liquid, right? Sure, but let's just put a piece of metal in here so that there's something to connect that wire to. And we've got that piece of metal hanging into that copper ion solution now. What should that metal be made of, do you think?
Copper.
Why copper?
Because that way there'll be real ions.
If I make this out of copper, copper will not react with copper ions. But every metal will conduct a current. And so if I make that electrode out of something that's not going to react with whatever's in this liquid, it'll be a good choice. It could be copper, it could be gold, it could be platinum, palladium. Gold, palladium, and platinum are a little too expensive, though. Copper's cheap. If I were to hang a piece of zinc in there, it would be just like up here. The reaction would take place in this little region right there, and it wouldn't do me any good. I couldn't get any electrons flowing. So now I've got it all set up. I can get electrons coming off of here, going this way, coming over to here, combining with the copper. The copper ions in the solution will then coat the outside of this little electrode, except for one problem. Yes? Never mind. It's not a closed circuit. If you remember back to when you studied circuits in whatever, middle school, first grade? Never? You never studied circuits? Oh no. Your challenge is to take a single piece of wire, a light bulb, and a D-cell battery and light the light bulb. You know how to do that. You know how to make a closed circuit, right? This is still an open circuit. See this big gap right here? There's a bunch of air in between these. So somehow we're going to have to connect these two. And so the way we're going to do that is we're going to put a bridge in there. And that bridge has a job to do. That bridge has to conduct ions from one cell to the other cell. Why does it have to do that? First of all, we've now closed the circuit. We have a big loop. We've got electrons forming on this electrode over here. They're flowing through the light bulb. They're going over to this electrode over here. The copper ions in solution will be attracted to the buildup of negative charge that's happening on here, on this electrode. And so they'll coat the outside of this thing. But what's happening to the solution on your right now? Copper ions are coming out of the solution. So what's the charge in that solution now? Not positive, because it's losing positive ions. It's becoming negative. There has to be something else in there. What do you think's in that beaker? How about something like copper nitrate? Take a copper nitrate solution, dump it into the beaker, I get copper ions. And nitrate ions, and we don't care about nitrate because all nitrates are soluble. So we're building up nitrate ions. What do you think happens to the nitrate ions? Well, over here, what's happening? The zinc metal is giving up a couple of electrons and making zinc ions. So we're increasing what's happening to this electrode. Whoops, I lost the whole thing. This electrode is going to start dissolving. So after a period of time, what started like this is going to start to eat away. You're going to start dissolving that zinc electrode, and you're going to build up positive charge in this cell, and you're going to increase the negative charge in this one. So in order to get those two things to balance, we've got to have cations flowing this way and anions flowing that way. Now I realize there's a lot going on there. Simplify it down. On the right-hand side, we've got zinc electrode. That zinc electrode is dissolving to give me zinc ions and some electrons. So as it loses electrons, the zinc ions are going to build up inside that beaker on the right. You can't have a positively charged solution. It has to maintain its neutrality. So if we've lost negative charge to electrons flowing through there, we've got to get negative charges from somewhere. On the left-hand side, the copper ions that are in the solution are starting to coat the outside of the electrode that's on the left-hand side. As we remove positive charge, we've got extra negative charge. So if we can get the negative charges to move from one beaker to the other, and we can get the positive charge to move the opposite direction, we can maintain a balance in this, and this whole thing is one big circuit where everything's traveling in a big circle. Now we've got a complete cell. We've closed the circuit, and we can actually, here we get to have some fun, Mike, right? Light the light bulb. It's so nice to have colors in here, right? I know, you don't have colored pens. Every single electrochemical cell is going to be built on the principle that says we want to make a complete circuit. We want to have enough electrochemical difference between the two different metals in order to generate the voltage we want. And we have to maintain neutrality of the solutions, and so we have to allow ions to move. This thing in the middle here, I called it a bridge, is a salt bridge. It allows ions to travel between the two half cells. You've got one cell that has zinc in it and one cell that has copper in it. If I go back to that picture there, why did you have to have paper soaked in water or in salt water? You needed a way for ions to transfer between the two metals. And if you have a way to conduct the charge of the ions, you can also get electrons to flow. Now this battery that you've stacked these pennies and nickels and saturated paper together won't do you any good until you complete the circuit. So you've got to have something in there that's going to measure the voltage. You have to have a light bulb to light. Something's got to complete the circuit, because if you don't complete the circuit, you actually have this, which is just a short circuit. All a short circuit is you've reduced the length of distance that the electrons have to travel. Instead of forcing them to go through this light bulb, like in the bottom half here, we've shortened the path, and they can just jump back and forth between the copper ions and the zinc. And so there's a much shorter path for them to travel. Whenever possible, electrons are just like everyone else. You take the shortest path you can. And so making an electrochemical cell is all about making it do what we want it to do, optimizing the conditions, and preventing short circuits. All right, if we have to have a salt bridge, look at the lemon cell that's set up there. Now we've got magnesium metal and copper metal. It says we've got a voltage of 1.95 volts in here. Where's the salt bridge? The lemon. What's in the lemon? Citric acid. And so the citric acid is serving as a salt bridge in this case. How long will this thing last as a battery? Not real long. Because once you get it to the point where there is a polarization of the ions in the lemon, and it happens relatively quickly, this thing will stop generating voltage. The bigger question is, how do we know it's 1.95 volts? Well, what are the reactions that are going on? Let's see. Magnesium and copper. Magnesium, if I look on my handy dandy little table here, find magnesium, there it is, 2 plus 2 electrons goes to give me magnesium solid. The cell potential is negative 2.37 volts. The other half was copper. If I look on the table that's in our textbook that gives me all these half reactions, copper 2 is right here, and I can read the cell potential off the side here, and magnesium is here. Magnesium plus 2 electrons to magnesium solid, and I work my way across to get to the 2.37 volts. The way that you calculate what the cell potential is for these is I look up those two values. The data table will always be written as reductions. the data table for consistency, and so to keep and make them half as long as you would need, will always have reduction potentials. So we look these two things up. We know we have to reverse one of them to make an oxidation. We have to pick which one we want to reverse, and by convention, we want the cell potential to be greater than 0. There's nothing wrong with having it less than 0, but we want it to be greater than 0 for a spontaneous reaction. And those of you thinking ahead are saying, wait, didn't we talk about spontaneous in delta G? Yes, we did. We're going to relate delta G to E0 in just a few minutes. So if I want a positive value, and I've got a very large negative value and a negative value here, I have to reverse one of these. I'm going to reverse this one. So I'm just going to turn it around. And now the cell potential is a positive 2.37 volts. If I leave this one the way it is, I get 0.34 volts. And now I add them together. I get 2.71 volts. Theoretically, I should be able to get 2.7 volts of potential out of this pair of metals. That said 1.95. Why isn't it 2.7? First of all, what are the two things you have to have? What are the reactants in this reaction? Magnesium metal and copper ions. If I look at this picture, I see the magnesium metal, but I don't see any copper ions. Instead, I've got copper metal. But we have to have copper ions in order for it to work. Where do they come from? Well, we already said there's citric acid in there. The citric acid will dissolve enough of the metal so that we get the ions in there. And once we get some copper ions in there, then we can get that reaction happening. So now the question is, why isn't it 2.7 volts? The answer is this. The superscript 0 means it's at standard conditions. And they're just like before. 25 degrees C, 1 atmosphere of pressure, 1 molar solution concentration. So if the concentration of the solution is less than 1 molar, would you expect the cell potential that you measure to be greater than or less than this standard amount? Less than. You don't have enough stuff. And so anything less than 1 molar for this solution is going to make this cell potential be lower. Why do batteries die? Because the concentration of the ions goes down below 1 molar. As the concentration goes down, then the battery stops working. What if I say, what is the cell potential for a, let's do a zinc / iron battery. So I just want to use zinc and iron. That's what I have laying around. So I go back to my table. And I have to start, and I have to look through here until I can find zinc and iron. Well, there's some iron. Iron 3 going to form iron 2. That's 2 ions. How about if I keep going? I know I'm probably off the screen now. Here's iron 2. making iron solid. Let's take that one. I'll write it here, then I'll bring this up in a second. The cell potential for that is 0.44 volts. And I still haven't found zinc. There's zinc. Zinc plus 2 electrons to form zinc is 0.76 volts. So those are my two half reactions that I just picked two off the table. I want a positive cell potential, so I have to reverse one of these two reactions. If I reverse the second one, now the cell potential of that, whenever you reverse the reaction, you just change the sign. We'll leave the other one the way it was. And we add them together. And so that battery, if I were to make it, would generate 0.32 volts. Everybody okay with that? Nobody likes the fact, what, you mean I just look these up in a table and I write the values down and I reverse one? Yes, that's all you have to do. It's a good question. What if I take copper and silver? So I go back here to my table, and copper plus 2 electrons give me copper solid is 0.34 volts. And then I have to find silver on this list. Here it is. Silver ions plus 1 electron to make silver metal is 0.80 volts. Okay. So there's my two half reactions. I could just add them together now and get a positive number, but I have to reverse one of them. I have to have an oxidation and a reduction. So one of them is going to get turned around. In this case, I'm going to turn around the smaller one. So I'm going to leave silver ions to form silver solid. And I'm going to take copper metal to form copper ions and a couple of electrons. And when I turn it around, I change the sign. When I add them together, I have to multiply this one by 2 to get the electrons to cancel out. Now this is the part everybody hates. All I have to do is add the numbers together again. I don't multiply by the number of moles. Why not? Here's the relationship between the cell potential, E0, and delta G. Delta G is equal to the the opposite sign, times the number of electrons being transferred, times a constant, the Faraday, which has a value of 96,485 coulombs per mole, times the cell potential in voltage. If I were to double the reaction, I double the number of moles. I don't have to double the E. We all know that if I do 2 times this reaction, and I'm talking about delta G, I have to double the value of delta G. Well, the fact that we've doubled the number of moles is taken care of by N, and so I don't have to do anything to E in order to get the number of moles to change. It's taken care of for me. So whenever you multiply reactions by some amount, the cell potential does not change. It's still going to be a fixed value. The other way to think of it is, if I've got 1 mole of copper ions converting to copper metal, or 2 moles, the difference in potential between them is still the same thing. I just have more that I can move from one side to the other. But the energy difference between them is still the same. And so I don't have to worry about that. So you don't double them. What is a rechargeable battery? What do you think a rechargeable battery is? You can you increase the concentration? Mm-hmm. Mm-hmm. Here's a rechargeable battery. It's one that you all depend upon, or most of you, I think, depend upon regularly. A car battery is a rechargeable battery. As you're driving, you are recharging your battery. So, how does it work? The chemical reaction of a car battery, I can never remember it, so I always have to look it up. Don't worry, I will never ask you to tell me what is the reaction of this battery. I may ask you to explain how it works, but I'm never going to ask you to repeat or to memorize this. That's the one electrode. That's the other. If I take and I add those two together, I get lead solid plus lead oxide solid. And then let's see, 4H plus, 2SO4 minus, 2 minus, in equilibrium with 2 lead sulfate and 2 water. So what happens in a car battery? There's lead and there's lead oxide in this car battery. In this picture over here, this screen is coated with lead oxide. Lead oxide is a white powder. The plates here, these, are pieces of lead. So there's lead metal in there and there's lead oxide in there. Surrounding the whole thing, there's sulfuric acid. That's where the H plus and the sulfate ions come from. When you use the car battery, and the only time you use it is when you start the car, or if you've got the car off and you got the radio playing, you're using something electrical. So anytime you use the battery, this reaction is going to happen. The lead is going to react with the lead oxide and the sulfuric acid. You're going to make lead sulfate and some water. And you'll generate the current that you need. And the way the car battery is set up, you try to generate as much current as you can when you need it. You need a lot of current to start the car. You don't need a lot of voltage. This car, anybody know the voltage of a car battery? 12 volts. What about is it on the picture? Oh, look at that, it's 12 volts. What if it's a motorcycle battery? 6 volts. Actually, this reaction is 2 volts. The only difference between a motorcycle battery and a car battery is that a car battery is 6 cells lined up in series. And so you've got 2 volts added to 2 volts, added to 2 volts. If you connect them in series, you get 12 volts. A motorcycle battery is only 3 cells connected in series.
Wait, how does that work? And the other one, you don't multiply the other one with silver?
Now these add together when we have different, now we're stringing together 2 batteries. Now we're not doubling a reaction. We're taking one battery, one cell of a battery, adding it to another one, adding it to another. And so we're adding all these voltages, okay? Now the way you make this thing reversible is, when do you recharge your battery? When you're driving. What's happening when you're driving? The alternator, that thing that you hear about every once in a while, is taking the motion of the engine, the alternating current, and driving this reaction back this way. If it goes from left to right, it generates 2 volts of potential. If you push it the other way, if you put 2 volts of energy into it, you can force it back the other direction. So what we take the lead sulfate and the water that are in there, we add 2 volts of energy, and we push this thing back the other direction to recharge it. The problem is, it's not selective. In other words, when these 2 things react, you don't necessarily get one lead oxide and one lead. You may get more lead oxide, or you may get more lead. Yes, the chemical reaction says this, but at some point, it's not going to be nice and even. Or what will happen is, you'll get buildup of lead oxide on this, so this cell is no good anymore. Now, if you're old enough, you know that they used to allow you to put water into these things. You'd refill the battery. They're sealed now. You don't have to anymore. But the reason they added water is because this thing also heats up. And when it heats off, the water boils off. And if there's no water in there, guess what happens to your battery? It goes dead. And so you add water and you can start to use it again. So a rechargeable battery is just one that we can send back the other direction. Now, why the heck then aren't these batteries rechargeable? And we'll talk about that on Wednesday.
For the next test,
Yes.
ambulance uses 4.
An ambulance uses 4 batteries?
Front to the back.